So, we will look at some of the mathematical fundamentals that are necessary for data science. Before I start, if you have any questions from last week, feel free to ask me. I will answer, and then we can start today's session. I will give you just a minute, and if I see any questions, I will answer. Otherwise, I will go on and start today's session. Okay, so if there are no questions, let me start today's session. As I mentioned last week, we are doing this course for 6 hours, and in the last 2 hours, I talked about what data science is, what are the different things that one does in a data science project, and some case studies to explain the kind of things that one can do with data science. In this class, what I am going to do is I am going to look at the mathematical fundamentals that are important for data science, which would be basically linear algebra, a quick recap of linear algebra, then statistics, and finally followed by optimization. So, these are 3 modules which are very important for solving data science problems. So, let me start with linear algebra and ask the question, why do we need to worry about linear algebra for data science? Linear algebra is a very important component of data science. Basically, it allows us to understand relationships between variables, and since we are looking at how data together can be used to identify meaningful solutions, it is of critical importance that we understand the relationships among variables. Linear algebra again could be taught in 2 semesters in all its detail, but since we are going to do just about 30 to 40 minutes of linear algebra, what we have done is we have picked out the most important ideas in linear algebra that are useful for data science. And there are many more ideas which are useful when you look at more involved data science algorithms. But here, to give you an idea of what might be useful in this first data science course, we are going to focus on ideas such as rank of a matrix. What do we mean when we say a null space of a matrix? We will talk about solutions to linear equations, and we will introduce you to the notion of hyperplanes, eigenvalues, eigenvectors, and so on. So, why should one look at matrices in data science? Typically, if you look at data, any process or any phenomena that you are trying to analyze using data science algorithms will have several variables of interest. So, let us assume there are about 10 variables of interest, and what happens is when you have these variables, there are many samples of these variables. Let us say I have 100 samples. That basically means each sample I have 10 values for this 10 variables, and I have 100 such samples. So, that means I have 1000 pieces of data that is of relevant to this. Data can be organized in a matrix form in terms of rows and columns, where the rows of the matrix could represent samples and the columns could represent values of variables in each sample. So, basically if you go across a row, then you have the values of these variables for a particular sample, and if you go down a column, you will see the value for a particular variable in the various samples. Now, the interesting questions that one could ask are the following. Supposing you have 10 variables, you might want to know if all of these variables are dependent or independent of each other. So, this is answered by the notion of a rank of a matrix. So, what this says is, if I have variables and samples, let us say I have 1000 samples and 10 variables, then I have organized this matrix where the rows of matrix represent samples. So, there are 1000 rows, and the columns represent values of variables in samples. Since I have 10 variables, I have 10 columns. So, now I have a 1000 by 10 matrix. I want to know in all of these samples if these variables are related or completely unrelated to each other. Rank tells me the answer to this, and basically if the rank is 10, then that basically means that all of these variables are independent of each other. Keep in mind that we are only talking about linear relationships in this module. So if the rank is 10, that basically means that all of these variables are linearly independent. In other words, if value for each, even one variable is missing, you cannot guess that from the other variables. However, let us say if the rank of the matrix is 5, and remember we are talking still about the 1000 by 10 matrix, then that basically means that 5 of these variables are related to other 5 variables. It could be any 5 related to anything else. In other words, what one could say is, if you give me 5 values in a sample of 10 variables, I can infer the other 5 variables from the 5 data points that you have given. So in each sample, there are only 5 independent pieces of information that are available, and the remaining are dependent on these. So this is the notion of rank, and this is why rank is very important. Now, in any software that you use, it's very easy to calculate rank. For example, if you were to use MATLAB, you just do the matrix, define the matrix, and then simply say rank of the matrix, it will tell you what it is. Now the question is, okay, let us take this 1000 by 10 example and we figured out that the rank is 5, right? Then we might ask, what are the relationships? How do I find the relationship? So as I mentioned before, rank of a matrix refers to the number of linearly independent rows or columns of the matrix, and in this case I am talking about 500 by 10. Rank of 5 would mean 5 variables are independent. The other 5 variables can be calculated as a linear combination of 5 independent variables. Okay. So when we identify the rank, it has several advantages. The most important advantage is that we could work with reduced set of variables, right? So if I have 10 variables, if I can always calculate 5 variables as a linear function of the other 5 variables, I can simply work with 5 variables. So this does not seem like much reduction for this problem. But imagine that you have, let us say, thousands of variables that come in, and then you want to kind of visualize what is happening. So clearly you cannot plot a 1000 variable plot. So if you find out actually the rank is just 2, that basically means only 2 variables are important. The remaining variables can be calculated as a combination of these. Then you could actually plot a couple of variables, important variables, to understand what is happening. So reducing the set of variables is useful in data science. So rank of a matrix, the first concept in linear algebra, which is very, very useful. Okay, I would encourage you, as I mentioned before, you can think of these lectures as giving you a feel for this field and things that you should focus on when you do your own independent study to understand this more. Now the next concept in linear algebra that is of importance is the null space of the matrix A. So if I have a matrix A and I have vector B, a null space of a matrix is the collection of vectors such that A times B equal to 0. Now from linear algebra, it's a well known fact that the number of vectors in the null space will be equal to whatever is the number of columns minus the rank of the matrix. So if we take the previous example where we said we have 500 samples and 10 variables, and we said the rank of the matrix is 5. So we initially had a 10 column matrix of which the rank is 5. So in the null space there will be 5 vectors, 10 minus 5. Now if the rank is 10, that basically means that there are no vectors in the null space. So the only vector which is in the null space is a 0 vector. For example, if B is 0, then that will satisfy this equation. So that's the only vector in the null space. However, if the rank is something other than 10, then the number of columns minus the rank will tell you the number of linear relationships that are there in the matrix. So in some sense, that the number of vectors in the null space basically denotes the number of linear relationships between variables. More interestingly, the null space vectors directly provide us linear relationships among variables. This is because if you notice this equation, AB is 0. So what this means is if I find a vector B such that AB is 0, what we are saying is I have a matrix like this, I have B, and on the right hand side I have 0. That means this is a 0 vector. What this says is that if I take a particular sample and multiply by this vector, it is 0. If I take the next sample, multiply by this vector, it is 0. If I take the next sample, multiply by this vector, it is 0, and so on. Since this vector has to multiply each row and make everything 0, that basically means that each of these vectors identify a linear relationships among variables, right? So for example, if I have x1, x2, x3, x4, x5 as the 5 variables, then if I take a vector, since it multiplies this and gives us 0, that basically means b1 x1 plus b2 x2 plus b3 x3 plus b4 x4 plus b5 x5 is 0. This basically gives me one relationship, and since this is true for every sample, it is a universal relationship among all the variables in all of the samples. So that gives me one linear relation. Now if I take a 500 by 10 matrix which has 10 variables and I have identified the rank as 5, that means there are 5 vectors in the null space. That means I have identified 5 relationships, which is consistent with the notion of the fact that I need to only give values for 5 variables, which is the rank. The remaining 5 variables can be calculated automatically. How would I automatically calculate those 5 variables? That is through those 5 relationships. So the notion of null space is a very powerful idea, and it helps us directly compute the linear relationships among these variables. So in terms of solving linear equations, if you summarize this, what we have done is we have understood from a matrix how many linearly independent variables are there, and we also can directly identify the relationships that exist between these variables, so that if given only a subset of variables, I can use the remaining relationships to calculate the remaining variables in the sample, right? So that is consistent. So I can completely characterize the data using these linear relationships. So then the natural question is, if I have a set of linear equations, how do I solve the equations, and what are the different cases that we need to worry about? So this is what we are going to see next. So before we go on, if you have any questions on whatever we have seen till now, feel free to ask me, I will answer. Otherwise, we will go on to this case. Okay. So if there are no questions, then I will proceed to the next step. So when I have a set of linear equations, so each equation represents a relationship among variables. It could happen in linear algebra that I have the same number of equations and variables. That is what I call as case 1. There are cases in data science where we need to solve the set of equations where the number of equations are greater than the number of variables, and there are also cases where we might have to solve the set of equations where the number of equations less than number of variables. So I just want to explain what happens in each one of these 3 cases. So when I have number of equations to number of variables the same, that basically means if I assume A is an m by n matrix where m is the number of rows, n is the number of columns, this case of number of equations equal number of variables is m equal to n. In this case, if all the columns of A are linearly independent, or if A is full rank, or if the determinant of A is not 0, then there is only one solution for this set of equations, and that solution is given by x equal to A minus B. Now this is straightforward. In the case that A is not full rank, that basically means if I have many equations and I have a right hand side, when A is not full rank, that basically means some of these equations can be written as a linear combination of the other equations. So for example, if you have 3 equations, equation 1, equation 2, equation 3, only 2 equations are independent. It might be possible that equation 3 is basically equation 1 plus equation 2. So in which case, if I get this A matrix, which would be 3 by 3 in case of 3 variables, the rank of the matrix will just be 2. So there is one relationship that exists. So in this case, there are 2 possibilities. One is there are no solutions to this set of equations. This is simply because if I had a B1 on this side, B2 on this side, B3 on this side, which is the right hand side, since equation 3 is equation 1 plus equation 2, If it happens that B3 is also B1 plus B2, then this equation becomes redundant. So this equation can be written as a linear combination of these two equations. So now you have two equations in three variables. In this case, you will have infinite number of solutions. Because you have three variables and two equations, you can arbitrarily pick a value for one variable, and the other two variables you can directly calculate. And you can pick an arbitrary value for one variable in an infinite number of ways, and each one of those will give you different solution. However, if B3 happens to be not equal to B1 plus B2, in this case what will happen is this equation will be inconsistent with these two equations. So no one solution can solve all of these equations at the same time. So this is the case for where m equal to n. The second case is where you have number of equations greater than number of variables, that is m greater than n. So this is a case where let's say you might have one equation in two variables x1 and x2, another equation in two variables, another equation in two variables, and so on. Now take the case where you have three equations in two variables. Now you can ask what will happen here. In the most general case, this will not be solvable. That is simply because if you take these two equations, you already have two equations for two variables. You can solve these two equations and get an x1 and x2 value for this. Now there is really no guarantee that the third equation, when you plug in this value of x1 and x2, this x1 and x2 satisfies this equation, right? So basically in many cases what will happen is you will have no solution for this case when you have many more equations than variables, right? Similarly, you could actually take these two equations and get an x1 and x2 which solves both of this, but there is no guarantee that will solve this. Or you could take this equation and this equation together and solve, and then put the solution into this, and there is no guarantee that this equation will be solved. So this is in general can be viewed as a no solution case, but still you will learn later when you do a lot more data analytics that this is a case that is encountered very often. Let me give you an example. There are always linear relationships that we assume between variables. That basically means that there are only two parameters that we can estimate. So for example, if I say a particular variable y is linearly related to x, I can write something like this. Now I have only two variables that I can actually identify. But in general, for problems like this, you will get the data where you have many y values and many x values. Now each one of these can be thought of as an equation. You have many equations, but only two parameters b0 and b1 that you need to estimate to solve all the equations. In general, it will not be possible. What you do is you think of some form of optimization to solve this, and we will see what that is. So what we do here is, supposing let's take the case of let's say I have a1 x1 plus a2 x2 equals b1. I have c1 x1 plus c2 x2 equals b2. I have d1 x1 plus d2 x2 equal to p3, right? So I have three equations, but I have only two variables. Clearly, if I pick these two equations and solve for x1, x2, it need not satisfy this. So one smart thing to do would be to say, look, let me collectively solve these equations where I minimize the error in each of these equations. So I could write, for example, something like this. I could write this equation in this form. I could say a1 x1 plus a2 x2 minus b1 is 0, c1 x1 plus c2 x2 minus b2 equals 0, and d1 x1 plus d2 x2 minus b3 equal to 0. So all I have done is I have moved these numbers to the left hand side. In the ideal case, you want this to be 0, but as I said before, you have only two variables. Using two variables, you cannot get three zeros on the right hand side. So what you do is you say, look, let's say if I find a solution x1 and x2, that there is some error or a residual that is there, which is r1, in the second equation r2 and the third equation r3. Now instead of saying I want r1, r2, r3 to be 0 at all times, what I could say is I will minimize r1 squared plus r2 squared plus r3 squared. Now if it is possible to find a solution in x1 and x2 that will satisfy all these three equations, then that will automatically make r1, r2 and r3 0. If it's not able to make r1, r2, r3 0, it will at least minimize the error in all the equations collectively. So we are not biasing the solution towards any particular equation, because we assume that all of these equations are important, right? So we don't want to say I want to solve only this equation or this equation, we want to solve all of them together. So this is an optimization objective that makes sense. The solution to this will be of this form. This is what is called a least square solution for the variable x. So this is a case of more equations and less variables. Now the last case is where you have number of equations less than number of variables. So this is an interesting case. So let's take a case where I have two equations where a1x1 plus a2x2 plus a3x3 is b1. I have c1x1 plus c2x2 plus c3x3 equal to b2. Now you notice that there are two equations but three variables. In this case what we could do is, let's say we pick some value for x3, right? So I actually arbitrarily say x3 is 5, okay. Now once I say x3 is 5, then these equations become the following: a1x1 plus a2x2 equal to b1 minus 5c1. The next equation will become c1x1 plus c2x2 equal to b2 minus 5c3. Now this is constant number. Now we have got to a situation where we have two equations and two variables, so you can solve for x1 and x2. So one solution is whatever we get for x1 and x2 and 5 for x3. Now there is no sanctity to the number 5. We could also say let it be 4, for example. Then you will have a1x1 plus a2x2 is b1 minus 4c1 and c1x1 plus c2x2 is b2 minus 4c3. Again this will become a constant number. You will find a solution for x1 and x2. So x1, x2, those values, and 4 would be a solution to the set of equations. So if you repeat this process, you could get infinite number of solutions for this. But if you are doing data science problem and someone gives you a problem, you cannot say, look, I'll get infinite number of solutions here. So you have to give one solution. Is there a rational way of choosing a solution? So in this case, what you could do is, there are infinite of number of solutions for x1, x2, x3. What you could say is, of all these solutions, I will find a solution which is minimum length. So just like in the last case we optimize r1 squared plus r2 squared plus r3 squared, here I'll optimize x1 squared plus x2 squared plus x3 squared. I know that this optimization problem definitely has a solution because there are infinite number of solutions, but among those infinite number of solutions I am going to pick one solution which minimizes this norm of the solution. Now if you do some matrix manipulation, so this will be the form of the solution for this. So we saw the three forms. This is the form when you have more variables than equations. We saw this as the form when you have more equations than variables, and this is the form when you have the same number of equations and variables. Now one interesting question is, would it be possible for us to combine all of these results into one nice result? Otherwise we'll have to say is the number of equations more, number of the variables more, and so on. So we got to keep asking this question. So is it possible to put all of them together in one elegant result? Yes, you can do this. This is what is the notion of pseudo inverse. So irrespective of whatever is the size of this A matrix, we can write X always as pseudo inverse B with the correct definition of pseudo inverse, and most of the software packages that one would work with will have a command for pseudo inverse. The beauty of the pseudo inverse is, if the equations and variables are the same, the pseudo inverse and invertible, pseudo inverse will be A inverse. When the equation and variables are different, number of equations and number of variables are different, depending on the two cases that we discussed, the pseudo inverse will automatically find the right solution. So that is the importance of this. So this is some basic equation solving in linear algebra that is very, very useful in data science problems, because in data science problems we are largely looking at how to find out relationships among various variables. Okay, so I'm going to go on to the next aspect of linear algebra, which has to do with the notions of distance, hyperplanes, dot products, and so on. So before I do that, I'm again going to pause for a couple of minutes for any questions that you might have, and I'll be happy to answer questions. Okay, so I will continue on, and feel free to, I guess you can raise your hand anytime to ask questions, and I'll be happy to answer anytime you have a question. So the next thing that we are going to talk about is a more geometric view of some of the things in linear algebra that are useful when we think about data science. The previous part of linear algebra, we talked about solving equations and so on, which basically is a very equation oriented view of linear algebra. The reason why we are also interested in the distance and geometric view of linear algebra is because of a class of problems that we solve in data science, which are called classification problems, which basically says if you give me data for different classes, let's say 2 classes, and I get you a new data point, you want to classify this data point to one of the 2 classes, and that uses notion of distance. So I am going to explain what this notion of distance is. To do that, we have to start by saying, okay, we will define what is called a length of a vector from origin. So it's easy to explain these things in 2 dimensions. So I'm going to do this in 2 dimensions, but the same notions are directly applicable in multiple dimensions, right? So if you had, let's say, a data point x1, x2, so we want to know what is the distance of this data point from the origin. So if you have x1, x2 axis, this data point is sitting here, which is x1, x2. The distance from the origin is a straight line that you're going to connect, and the length of this straight line will be the distance. And the formula for this is root of x1 squared plus x2 squared, which can also be written as root of x transpose x. Okay. So this is the distance of a point from the origin. Now if you have 2 points, let's say one here and one here, and if you want the distance between these 2 points, then that is given by this formula, which is basically x1 minus x2 transpose times x1 minus x2 root. Okay. So this gives you the distance between these 2 points. Now when you think of each of these samples, let's say I have these variables which have values, and let's take one sample. And when you think of, let's say, in the previous slide, if you notice, when we think of x1 and x2, we can also think of this as a vector. Now what you could say is, whenever I have a vector of this form, this vector can be written as a linear combination of other vectors. As an example, if I drop a perpendicular to this and then I do 2 vectors, then I can say this vector is a sum of this vector plus this vector. So you can think of these vectors as linear combinations of other vectors. So this is very useful to analyze these vectors. So for example, in n dimensions, we just talked about 2 dimensions. Let's say in a 3-dimensional room, you can write any point in a 3-dimensional room as a linear combination of 3 vectors. So for example, if you look around yourself and if you look at the room and then say you look at the floor, and then you take one vector on one wall, the other vector on the other perpendicular wall, and the third vector which is coming out of the floor, then those 3 vectors are enough to represent any other vector in the 3-dimensional room. So you can always write any other vector in the 3-dimensional room as a linear combination of these 3 vectors. So this is what I have shown here. For example, if you have v1 and v2 as 2 vectors, I have a vector which is kind of projecting out of this. First, I can write this vector as a linear combination of this vector and this vector, which is just an addition. So I can add x hat and n, I will get x. But since x hat falls in this v1 and v2, I can write x hat as a linear combination of v1 and v2 because it is falling in the plane that is formed by v1 and v2. Now if this is coming outside, it is an orthogonal projection, then this x hat is called the projection of this vector onto this space, and that projection is easily calculated using this formula here, where x hat is given by the projection onto v1 and projection onto v2 multiplied by the vector directions themselves. So this is a very useful concept because this is something that we use whenever we try to do classification. As I mentioned before, we talked about ensuring that we understand the geometry of these equations, because I said we are interested in classification problems. So how do we understand the importance of this from a classification viewpoint is shown in this slide here. What we are trying to show here is, for example, let's take a problem where I have data which is for 2 variables. Let's say think of any two variables. Any two variables could be, for example, let's take a very simple example of the fact that we want to characterize if someone would like North Indian food or South Indian food, and maybe we just pick two characteristics of that person and then say, okay, I'm going to take 100 samples, I'm going to survey 100 people, and then for each one of these people that we have surveyed, we are going to put two of the characteristics. One could be whether they are North Indian or South Indian, another one could be one particular question to which they answer, whatever it might be. And then for each of the samples we say there are these people who are likely to prefer South Indian food, and these are people who are likely to prefer North Indian food. Okay. Now there is a new person who comes in whose value is this in terms of these two variables. Now the question is, I want to classify whether this person will like South Indian food or North Indian food. Okay. So that's a very simple question that I can ask. So how do I classify this person? So to do that, what in classification we do is, this is data that I already have, this is data that I already have. What I do is I come up with what I call a decision surface which separates these two data points. So if you talk about this decision surface, this is a line where you could say to this side of the line are people who prefer South Indian food, and to this side of the line are people who prefer North Indian food. So the line itself should have some characteristics which will allow us to do this. So that characteristic is the following: for any line that you define, depending on how you define that line, you can always show that the way you have written that equation, one half plane at which is one side and the other side. So if I have an equation of this form, based on how I define, there will be a negative half plane and a positive half plane, and whenever there is a point to this side of the line and I substitute that into the line equation, then if the point is to this side, it will always be negative, and if the point is to this side, it will always be positive, and if the point is on the line itself, then it will be 0. So this you can show, and this is very useful in data science, because when I get a new data point which has this couple of characteristics, I put this into this what I call as a decision function, which is this, and I say if this decision function is negative, it belongs to class 1, and if this decision function is positive, then it belongs to class 2. In this example that we talked about, class 1 could be whether you liked North Indian food. If you like North Indian food, you could be class 1, and if you like South Indian food, you could be class 2, and so on. So this proof how this negative half plane happens, it all depends on these distances and the previous definitions we had, but it is important to understand that this notion of half planes is very useful in data science from classification problems viewpoint. Now I am going to go on to the next important idea, which is the notion of eigenvalues and eigenvectors. I will give you a brief idea of why we are interested in this. Remember, we talked about Ax equal to 0, where x then is in the null space of the matrix A. Now when we think about Ax equal to b, I said that each of these vectors you can think, each of these set of variable values you can think of as vectors. So when you look at Ax equal to b, supposing I have, okay, so if I say x is here, b is here, okay, I told you that each of these could be thought of as vectors. Now what we are saying is, when I multiply this x by a, it transforms this vector to this vector b, right? So that is what this Ax equal to b equation says. So when I pre-multiply this x by a, then there is some transformation occurs and this x vector becomes b vector, right? You can think of this matrix multiplication as this vector transformation. Now an interesting question to ask is the following. So for every matrix A, are there some vectors which when I linearly try to transform it using A, it does not go into a different direction, but it stays in the same direction. So what we are asking is the following. So if I have this vector x, and when I multiply by A, it does not go to some other direction, but it either decreases but stays in the same direction, or increases, stays in the same direction. So that can be written mathematically as Ax equal to lambda x, and notice here lambda is a scalar and x is the vector. So you see the direction of this and this are the same because both are in x direction. But if lambda is negative, we have gone in the opposite direction. If lambda is positive less than 1, we have shrunk the length. If lambda is positive greater than 1, we have enhanced the length of the vector. Now, this is a very important equation which is used in several places in data analytics. When I can find a vector with a constant like this for a matrix, then I call this x as the eigenvector and I will call this lambda as the eigenvalue. So, this is a very useful concept that is used in lots of linear algebra, lots of data science applications, and that is shown here in terms of a picture. So, I have an x, and if lambda is greater than 1, I basically expand this or shrink this. These special vectors are called eigenvalues and eigenvectors. So, I am going to stop here in terms of the linear algebra part of this class. Again, let me emphasize that what I am trying to do is basically give you a very intuitive feel for some of these ideas. What I would really like you to do, if you are really interested in data science, you should go and pick up more understanding of these materials, and once you have a decent understanding of these materials, then it is easy to get into this field and start understanding algorithms and so on. Again, I am going to give a short break for any questions that you might have. If there are no questions, then I will go on to the next portion, which is statistical modeling. Okay, so there is a question where someone is asking, can I explain orthogonality first and then in terms of data science? So, I will answer both of these questions. So, orthogonality basically means if I have two vectors, the angle is 90 degrees, it is called orthogonal. From a linear algebra viewpoint, orthogonal vectors are such that x1 transpose x2 is 0. So, if this is true, then these vectors are orthogonal. If x1 transpose x2 is 0, then that also means x2 transpose x1 is 0. Now, so this is basically the definition of orthogonality. Now, if you ask why is orthogonality important from the data science viewpoint, the reason is the following. For example, if I have, let us say, two basis vectors v1 and v2, and I am going to write some vector y as a function of this v1 and v2. If these vectors turn out to be orthogonal, then the computation for this becomes straightforward. I can multiply on the left hand side by v1 transpose y is c1 v1 transpose v1, and when I do v1 transpose v2, that goes to 0 because I have chosen v1 and v2 to be orthogonal. So, c1 is directly v1 transpose y by v1 transpose v1. Similarly, c2 will be v2 transpose y by v2 transpose v2. So, what happens is when you have many basis vectors and you are trying to write any vector as a linear combination of these basis vectors, what you can do is once you write y as a function of v1, when you add another vector to explain y better, you do not have to change your original v1 that you had. Okay. So, if I say y is c1 v1, I first calculate only for c1. If I keep adding this in terms of basis vectors which are orthogonal, when I do c2 v2, I do not have to go back and recalculate c1 because c1 is independent of c2, right. So, as long as this is orthogonal, then it makes it easy for me to keep adding this. So, when you have large number of variables and large number of directions that you are working with, then this becomes a very important concept. This orthogonality allows you to build better and better explanations for y without going back and changing what you had originally already done. If this were not orthogonal, then this would be a problem. You have to take both of them together and do this. So, that is the answer to the question of orthogonality and why is it useful in terms of data science. Anything else? Does that answer your question? Okay. So, if there are no other questions, I will move on to random variables and probability distributions. So, like I said before, linear algebra is one important field or concept that one needs for data science. The other interesting concept or important field which is very used in data science is statistics. So, why are we interested in statistics in data science? Typically, variables that we have been talking about till now in terms of equations and so on, we always talk about them as deterministic variables. So what we mean by deterministic variables is that these variables take a particular value which you are confident about. But in many cases in real life, you cannot just work only with deterministic variables. There are also random variables that you need to work with. So in simple terms, deterministic variables are variables which are fixed or can take only one known value at a particular time or experimental condition. So if you keep repeating that, if it's a deterministic variable, if everything else is the same, the value for the variable will keep coming out to be the same. So it is known precisely with no error in measurement and can be predicted exactly. Random variables are variables which can take many values at a particular time or experimental condition. In other words, everything being the same, if you measure the same variable multiple times, each time it will have a different value. And that different value is one from several possible values that the variable can take. So you cannot really precisely predict the variable, but you could basically say what is the probability that the variable will take some value within certain range. And this is very an important concept that one needs to handle in data science, because randomness are things that we cannot exactly predict are all around us in terms of phenomena. So if you think about what are the sources of randomness in data, so there could be two sources of randomness. One could come out of lack of knowledge of the data generating process. So if I have a model and then I am predicting something, the model could be erroneous and I cannot exactly get it, so that's called model error. And the other type of error is if you are measuring some variable, you are not able to precisely measure that variable because of errors in your sensors, so that is called measurement error. In general, in data science, in many cases, we handle variables which have both a deterministic part and a stochastic part. The deterministic part is the outcome of a very well defined precise process, and the stochastic part is an outcome of randomness, and where you cannot exactly predict what that stochastic part would be, but through some notions of distributions and so on, you can say I will be able to predict what the probability that the variable will take a value in a certain range. Now, deterministic variables are usually characterized by functions, so whatever we have been talking about. And random variables, when you say I don't know what the value it will take, then there is a real question of how do you work with these variables, how do you make meaningful conclusions when you have variables of this type. What happens in those cases is that we use a notion of distribution or probability distributions, where while we claim that I cannot precisely say this variable will take a particular value, if you give me a range of values for a variable, I will tell you what is the probability that the variable will take that value. In general, when I have stochastic variables, the predictable part is characterized as a function and the remaining part, error, is described using probability distribution. Since we talked about probability distributions, let's look at some probability basics. Just quick run through of some of the concepts that you might already have heard about. A random phenomena is a phenomena whose outcome is different every time the phenomena occurs under ideal conditions. So supposing you were to throw a coin, there is no one who can for sure say I will get a head or tail, right? So every time you throw a coin, you could get head or tail, right? But when you are at the act of throwing the coin, for sure you cannot say it will be head or tail. Now if you look at just this one toss, the possible values or the possible outcomes are head or tail. So that is what is called the sample space for one throw. Supposing you were to flip the coin twice and then say what are the possibilities, in this case the sample space becomes bigger, where you could have head head, head tail, tail head and tail tail. So there are 4 possible scenarios here. An event is a subset from sample space. So for example, if I have this as the sample space an event is a subset from that, which could be head, tail, tail. So here this is an event where we are asking, when I flip the coin twice, both times I want the same outcome, then what are the possible outcomes? So since we say I want the same outcome, it could be head, or tail, tail, which is a subset of the sample space. So when two events are mutually exclusive, okay, the example is something that is given here. So we call events as mutually exclusive if the occurrence of one event excludes the occurrence of the other event. So if one occurs, the other one cannot occur at all. So that is what are called mutually exclusive events. Independent events are events where the occurrence of one event has no influence on the occurrence of the other event. Okay, so those are two other concepts that are used in probability. Now, so we said any time we do an experiment, there is an outcome that comes about. Associated with every outcome is a probability of that outcome occurring. So in the head or tail example, if the outcome is head, then the probability of that outcome is half, 0.5. The outcome is tail, the probability of that outcome is 0.5. Now if you take the next example that we talked about, where I am tossing the coin twice, then the sample space is this, and then if you say what is the probability of the outcome where both the results of the coin flips are the same, then that probability is also half, because whenever it's head, or tail, tail, both the outcomes are the same, both are the same. So that is our event that we talk about. So that will have a probability 0.5 and so on. So the probability can be interpreted as the function of times outcome occurs if the experiment is repeated a large number of times, and whenever we talk about probability, it has to satisfy certain axioms. Probability of all events put together is 1. That means if you have, let's say, 1000 possible events, whenever you do an experiment, it has to be 1 of the 1000, right? So that is what is given by this equal to 1. The probabilities are non-negative and less than 1, and probability of A union B is probability of A plus probability of B if A and B are mutually exclusive events. That basically means that if A occurs, it precludes B, and B occurs, it precludes A, then probability of A union B is probability of A plus probability of B. There are several other rules that you can prove in terms of probability, which are all usually easily visualized in terms of Venn diagrams. For example, probability of A complement is 1 minus probability of A. Probability of A union B, in the general case, it's probability of A plus probability of B minus probability of A union B. Now, if these two are independent events, then probability of A intersection B will be probability of A times B, so which can be substituted here. And we saw if A and B are mutually exclusive, A and B cannot occur together, so probability of A intersection B will be 0. And we saw in the previous slide probability of A union B equal to probability of A plus probability of B if A and B are mutually exclusive events. Okay, so all of this ties in together. So these are simple rules for probability that one can look at. Then there is also the notion of conditional probability, or the Bayes formula, which says if you want to identify a probability of an event A occurring given that B has occurred, then you could write this formula which says probability of A given B times probability of B has to be probability of B given A times probability of A. This is called Bayes formula. This is a very important notion because this is a notion that is used in lots of data science algorithms where classification is done based on a Bayes rule. We have one example here which you can go through to look at some very simple calculation using some of these notions of probabilities. Okay, we will move on to now probability distributions, where I talked about the fact that for a particular variable I cannot say that it will take a particular value, but I might be able to say a range of values what the probability would be that this variable will take in that range. Okay, so we will take again a few minutes break and wait for questions. If there are no questions, I will proceed. Okay, so we will continue. So we will look at probability distributions. So basically what probability distributions do is to be able to explain the probability that a certain variable will take a certain value or will take a value in a range of values. So for example, if you take a discrete random variable, the possible examples such as throw of a dice or a coin, and if it's a continuous random variable, you could have things like sensor readings, time between failures and so on. So associated with each of these random variables is this notion of a probability measure. So for a discrete random variable, we define what is called a probability mass function. It assigns a probability measure to every discrete outcome of the sample space. So in the case of coin toss, as we already discussed, heads or tails are the outcome, and the probability of head equal to probability of tail equal to 0.5 if it's an unbiased coin, right? So there is an equal probability of you getting either head or tail. This is how the probability mass function is generally defined for discrete random variables. For continuous random variables, however, what we do is we say the probability a continuous random variable will take any particular value is really 0, because if we say a continuous variable can take any particular value, then it becomes actually predictable. So for continuous random variables, what we do is we try and find out what is the probability that the random variable will take a value in a range between a and b, which is given by this integration, integral a to b f of x. This f of x is called the probability density function, and if the lower limit is minus infinity up to this, then this basically says what is the probability that this variable will take any value from minus infinity to b. This is what is called as a cumulative density function. There are different types of density functions that one comes across when one works with data science problems. Binomial is a well-known mass density function, which is NCKP power k1 minus p times n minus k. So for example, if you have the probability of obtaining k heads in n successive tosses of coin, one could use this, where p will be half. Now when n is very large, that is the number of successive tosses of coins you are doing is very large, then it is going to start looking more and more like a Gaussian distribution, which is what is shown here. Another distribution function that is frequently used, which we saw from the previous slide, is the Gaussian density function. Gaussian density function is of this form. The Gaussian density function is represented by two parameters. One is the mean mu and the other one is the variance sigma. Now you have to understand this function carefully. If you take a particular value and put it into this, it does not represent any probability because this is a density function. So the way you use this function is, if you say, look, I want to find out what is the probability that my variable will take a value in this region, then basically what you do is you find the area under the curve, and this area is what is the probability that this variable will take a value in this range. Now based on the probability axiom, if you do the whole area under the curve, that will go to 1, because the probability has to be 1 for at least one event to occur. So in continuous random variables, in comparison to discrete random variables, this is an important aspect to remember, that we always say there is a probability that the variable takes a value within a range and not exact probabilities of exact values that the variable will take. Now there are other probability density functions which are used. One is called the chi-square density function, which is of this form, and the picture corresponding to that chi-square density function is shown here. Now when it comes to data science, all of you would have seen this before. The two important things that one calculates for any data is the mean and variance. So this you would have seen many times. The reason why this mean and variance are important is because we normally assume that the random part of the data follows a Gaussian distribution, and the Gaussian distribution is completely parameterized by these two parameters, mean and sigma. These are also called as the first order and second order moment of the density function. Now if you give me sigma on mean and I exactly know what the distribution function is, then I can do all kinds of calculations in terms of what is the probability that a particular variable will take value in a range. More and above this, the notion of mean and variance is also very intuitive. For example, let's say take a road and there are many cars going and these cars are going at different speeds. Then if you want to characterize the traffic, one thing you could do is the traffic in general fast or slow is a question that you could ask. And if I have lots of cars going and lots of speeds at which these cars are going, how do I figure out whether collectively it's fast or slow? One thing you could do is you could take the average of all the speeds, and let's say if the average is 30 in one case, in another road the average is 60, then you can say in general the traffic in the second road is much faster than the traffic in the first road. So the mean gives you an intuitive idea of what is happening in general, right? So that's the reason why mean is a very important quantity. Similarly, variance tells you what is the spread, right? So if it says the mean is 30 but the variance is also 30, then basically what it says is while the average speed is 30, there are some cars which are really going very fast and there are some cars which are really going very slow. So how diverse is the data is in some sense captured by the variance. So the mean captures the average tendency of the data and the variance captures how much variation is there from this mean tendency when I look at all the data. So both of these seem to make very intuitive sense, and that is another reason why when you calculate this you get a feel for what the data is all about. Underneath this, of course, once you calculate these two, then you can actually characterize the distribution, and if you assume the distribution is Gaussian, then all you need are two parameters that are estimated to completely define the probability distribution. There are several other properties of Gaussian random variables which I am going to leave for you to read. Now this is an important slide. When we talk about data, remember we talked about many samples with large number of variables. Typically in an undergrad class, people are used to one variable calculation. So usually we calculate the mean and variance for one variable. But in data science problems, we are looking at multiple variables. So we define what is called a multivariate normal distribution. So if I have 10 variables, each of these variables will have an average. So mean itself is a vector which is going to give me the average of each of these variables. So if I have 10 variables, the mean will be a vector of the size 10 by 1, where each component tells me the mean of the corresponding variable. Now when it comes to variance, that becomes a matrix where you have your variance, single variable variance in the diagonal, and what we call as covariance, pairwise covariance in the off diagonal entries. So in the univariate case, mu is a scalar and sigma is also a scalar. In the multivariate case, mu is a vector and sigma is a matrix, which basically gives you the univariate kind of calculation and also gives you pairwise covariance numbers. So this is an important thing to remember. And look at this equation. This is how this equation changes when you have multivariate data. So we saw the univariate Gaussian in one of the previous slides. I'll show you this here. We saw this Gaussian distribution for the univariate case. The same thing when it goes to multivariate case looks like this, which is 1 by 2 pi over n by 2. N is the dimension of the vector, which is the number of variables you have in the problem. This is the determinant of the covariance matrix to the power half, and you have exponential this term. So this is the multivariate normal distribution. So let me stop here again and ask if you have any questions that you might want to ask. So let us continue. There is another important notion in data science which is very useful, which is called sample statistics, and let's explain what sample statistics is. We talked about random variables being discrete and continuous, and we talked about probability density functions or distribution functions for these random variables. However, you can calculate these if you know the entire sample space. So remember, in the coin toss, if you were to toss the coin twice, you know exactly all the 4 outcomes that are possible. But in many cases, the entire sample space may not be known. So if you do not know the entire sample space, then when you calculate the parameters of the distribution, they become only estimates of the truth, right? So parameter of distribution may not be known, so you might have to actually calculate that from the sample itself. So from a finite sample, you have to derive conclusions about the PDF and its parameters. What we need to do is we need to have enough samples so that the samples together are sufficiently representative of the entire space. So that is an important thing that we have to ensure. So the basic concept is population is the set of all possible things that could occur, right? So if you keep doing this experiment infinite number of times, you have certain outcomes. The collection of all of those outcomes is what we call as population. But clearly in real life, the population will not be available. So for example, if you take a road and then say I want to find the speed of cars in this road, population would mean from the time the road was laid till the time the road is removed, the speeds of all the cars that have gone through, right? But typically you're not going to get that kind of information. What you're going to get is you're going to go there and sample it some days, and then you're going to get only a sample statistic. So you only get a finite set of observations. So now you're going to make some conclusions, which is going to say, look, cars go in this road faster than the other road. That basically means you are making some conclusions about the population. You are not saying only this day the cars were faster and so on. So you are deriving conclusions about the population from the sample set. So for this you need what is called sample statistics. So there are two types of sample statistics. One is called descriptive statistics, where you could basically do these things in a very graphical fashion. You can organize and present data in terms of box plots, probability plots and so on. Or you could do numerically in terms of a mean, mode, range, variance, moments and so on. So these are all what we call as descriptive statistics. Inferential would mean, so this is descriptive in the sense that there is a variance formula here which you are simply applying. There is a mean formula here which you are simply applying. Mode, there is a formula that you are applying. Range is just looking at the data and say what is the min and max, right? So this is very simple calculations that you are doing from the data. Inferential would mean that you are going to make judgments about the type of distributions from which this data came and the parameters in the distribution and values of the parameter in the distribution. That is, this comes from a population distribution which is chi-squared or t-squared or f distribution, whatever that is, and you are also going to make judgments about the parameters in the distribution. So you are going to estimate parameters of the PDF. So this question of estimating parameters from the PDF and then looking at population distributions is called hypothesis testing. So there are several different plots that you can draw. These are all standard plots that you could do to understand the data. There is something called a probability plot. The actual thing is explained here, so you can read this and understand this later. So these are typical plots that one is interested in looking at. Scatter plot is another type of plot you can look at. So these come under descriptive statistics, where you are basically taking the data, plotting, calculating certain things and so on. So sample mean, a very simple formula is used to calculate sample mean. Sample variance, again this is something that you might all be familiar with. So those form the descriptive statistics, which is basically looking at plots and simple calculations. We move on to hypothesis testing. Hypothesis testing is a test that you do to make some judgments about parameters of a distribution, right? So for example, whenever you do hypothesis testing, there is something called a null hypothesis, which people call as H0, and there is something called an alternate hypothesis, which is H1. Null hypothesis or H0 is a default or status quo postulate, which will reject if the sample set provides sufficient evidence, right? So null hypothesis could be that the mean is 0. Now if you want to say the mean is not 0, I need to have really sufficient evidence to go away from null hypothesis. So typically we are testing for the null hypothesis. Now there is another hypothesis which is alternative hypothesis H1. This is the hypothesis that is accepted if the null hypothesis is rejected. Again, null hypothesis is rejected if you have sufficient evidence, and once we have that evidence, then the alternate hypothesis is what is accepted. So in general, the hypothesis testing procedure goes through this kind of sequence. First, you identify the parameter of interest, right? So whether it could be a mean of a population variance or a regression coefficient. Basically, when you do a linear regression, you want to get the parameters, values, and so on. So you first identify the parameter of interest which you wish to test. For each of these, you construct the null and alternate hypothesis. So null hypothesis could be, for example, a parameter takes a particular value, could be a null hypothesis. Now, you need to have enough evidence to see whether the actual value is different from this value that you have hypothesized. So that would be your alternate hypothesis. So once you construct a null and alternate hypothesis, you basically compute what is called a test statistic, which is purely computed from your sample set of observations. So you take your sample set and construct a test statistic. Now, if the null hypothesis were true, then you derive the distribution that this test statistic will follow, right? So if the under null hypothesis assumption, you say what would this test statistic follow in terms of distribution, then you use some thresholding to say I either accept or reject the null hypothesis based on comparing this test statistic to that threshold. So that is the basic procedure that one uses in hypothesis testing. Now you have to remember this is used quite a bit in data science. You have to remember no hypothesis test is perfect because all of these are based on set of observations which are random. The performance of the hypothesis test depends on the extent of variability in the data, the number of observations. The more observations, the better it becomes, the test statistic and the test criterion. So depending on what is your criterion, you will have to live with different errors in terms of type 1 error, type 2 error, and so on. So typically there are two types of errors that one talks about. So here is a table which explains this. So the truth is along the column, which is if I have a null hypothesis, the null hypothesis could be true or the alternate hypothesis could be true. These are two possibilities that are there. In terms of a decision, once you do the hypothesis testing, one decides to either accept the null hypothesis or reject the null hypothesis. Now, if H0 is true and H0 is accepted, then this is the correct decision. If H0 is true, H0 is rejected, this is the wrong decision, type 1 error. If H0 is false but it is accepted, then this is type 2 error, wrong decision again. And if H0 is false and H0 is rejected, this is the correct decision. So the probabilities associated with each of these decisions are given here, and you basically have to choose how strong you want your test to be. So you have to basically choose an alpha value that you are happy with, you are willing to accept, and then correspondingly you will have your type 1 errors and type 2 errors. Okay, so there are a few examples and summary of useful hypothesis tests that I have in the slides, but in the interest of time I have half an hour more where I want to introduce the next important idea of optimization, because it becomes very, very useful from data science viewpoint. So I am going to leave these slides for you guys to look at, and if you have any questions you can always post them and get them answered. Okay, so I am going to move on to optimization next. And if you have any questions, please feel free to ask me right now. Okay, we will continue. I just want to mention again, even though I am repeating myself, again statistics and probabilities and so on, we teach in multiple semesters. So we have looked at it in half an hour. So what I really want you guys to get out of this is that these are important concepts, these are basic ideas that you should go and read and follow up a lot more to understand better. These form the bedrock of data science, and you really need to, if you want to get into this field of data science, you have to really understand these things much better, right? So let's keep that in mind. And I'm going to do the last topic for today, which is fundamentals of optimization. And first I will kind of explain what is optimization, and then tell you why we are looking at optimization when we are talking about data science. Optimization problem is one that consists of either maximizing or minimizing a real function. And how do you maximize or minimize this function? By choosing what we call as decision variables, values for those decision variables. And while we choose these values for these decision variables, there is a set of values that these decision variables can take, which are called the constraints. So that is what an optimization is. So why is optimization relevant for data science? It is because we could use optimization to find the best functional representation for data, which is one of the important things that we do in data science. It can be used to find the best hyperplane to classify data. Remember the line I showed in terms of the North Indian, South Indian food. How do you come up with that line given data is an optimization problem that you can use. Why optimization for machine learning or data science? You can think of all machine learning algorithms as solutions to optimization problems. Even in cases where the original algorithm was not derived like that, you can still think of them as solution to optimization problems. Once you understand machine learning algorithms as optimization problems, you can more deeply understand the working of the algorithm, and you can also rationalize the working of algorithms, and maybe if you really get good at it, you can also develop new algorithms yourself. Now, when we talk about an optimization problem, there are several components of an optimization problem. One component is objective function. The other component is the decision variables, where we are trying to get values for the decision variables which will either maximize or minimize the objective function, and the constraints which are imposed on the decision variable. So these are the three main aspects of any optimization problem. Now there are several different types of optimization problems depending on the objective function, constraints and decision variables. If your objective function is linear and constraints are linear, we call that linear programming problem. If either your objective function or constraints become nonlinear, it's called nonlinear programming problem. There are very special class of problems where the decision variables are not continuous variables, but they are discrete variables that they take values either 0 or 1 or 2, 3 and so on, only integer values. Those are called integer programming problems. If the decision variable can only take values 0 and 1, then we call it binary integer programming problems and so on. You could have some variables which are integer and some variables which are real, in which case we call these as mixed integer linear programming or nonlinear programming problems, depending on whether your objective function and constraints are linear or nonlinear. So what I am going to do is I am going to introduce how we solve these optimization problems, and when you see some machine learning algorithms, then you will see how some of these ideas are translated to these machine learning algorithms. So we will first start with what we call as the unconstrained case. Basically here I have just an objective function, and that objective function is written in terms of the decision variables, and I am trying to optimize that objective function with respect to the decision variables. So here are the basics. So for example, if you have a function like this, so this is your objective function and x is your decision variable. So the decision variable can take any value on this real line. Of all the values it can take, we are interested in this one particular value x star, which is where the function attains its lowest value. So if you ask for an optimization algorithm to minimize this function, then it will say, okay, I am going to minimize this. That basically means I have to set x equal to x star, and at that point f of x will have f star, which is the minimum value this function can ever take. Okay, so that is the notion of minimization. Now in general, when you have functions, there is usually not only one minimum value. You take a look at this function here. So if you look at this, if you look in this local region, this value is the lowest value that the function can take at this value of the decision variable. But if you look at this locally here, then this is the lowest function value at this value for the decision variable. So in general, because we only look at it locally, both of these are called minimum, right? Because if I am sitting here, so think about sitting here, I have no idea that something like this is going to happen here. So when I look at myself locally, any direction I go, the function increases. So I would say this is a minimum, and this is called a local minimum, and this is called a global minimum. Now from your high school and college, you would have learned how to calculate this minimum. So very simple. If you have a single variable function, then the calculation is straightforward. So if I want to find the minimum point, then at that point you will know that f prime x has to be 0, and f double prime x has to be greater than 0. If this is the case, then we will say this point is a minimum point where f prime represents the first derivative and f double prime represents the second derivative. So for x star to be a minimizer of this function, we know the first derivative has to be 0 and the second derivative has to be greater than 0. So this is what we call as a univariate optimization. So I have a numerical example here which you can work out to see how this works out. Now, much like we made the distinction about single variable and multivariable in the statistics case, again when you come to optimization, you can talk about a single variable and multiple variables. Typically, the optimization problems that we are interested in are multivariate optimization problems, where I am trying to maximize or minimize a variable which is a function of several variables. So in the previous case, we had z is simply equal to f of x, and we said f prime x has to be 0 and f double prime x has to be greater than 0 for the point to be a minimum point. But what happens now when I have multiple variables? So how do I define minimum points? What you do in the multivariate case, and these slides tell you why this is true, but I am going to give you the result in the interest of time. So in the multivariate case, what you do is you calculate what is called a gradient. Okay. So if I have a function which is a function of x1 to xn, I can calculate the partial derivative of f with respect to x1, partial derivative of f with respect to x2, and so on up to partial derivative of f with respect to xn. Now just like how you had df by dx or f prime x equal to 0 in the single variable case, in the multivariate case what you do is this gradient grad f you set to 0. Okay. So if you have a function f and you have n variables, then when you set this to 0, you will get n equations. Dou f by dou x1, partial of f with respect to x1 is 0, partial of f with respect to x2 is 0, and so on, and partial of f with respect to xn is 0. Now we get n equations in n variables, so we solve this and then we will get a solution, and that solution is either a maximum or a minimum or what is called a saddle point, and we will see what is the test you do to find that out. Once you get a solution to this, what you then do is you calculate what is called a Hessian matrix. Much like, remember, the covariance matrix in the statistics case had your sigma squared and sigma 1, sigma 2 and so on the off diagonals. This also looks very much like a similar structure. You have dou squared f dou x1 squared, dou squared f dou x2 squared, and so on, dou squared f dou xn squared. These are in the diagonals, and in the off diagonals, if you take, this is the partial with respect to a pair of variables. This matrix that you construct, so if you have n variables, this will be an n by n matrix. This matrix you construct is called the Hessian, and if the Hessian is positive definite, then this point is a minimum point. If it is negative definite, then this point is what is called a maximum point, and if it is 0, or if it is neither positive definite nor negative definite, it is semi-definite, then we call that a saddle. So in terms of an overall summary, if it's a univariate case, the first derivative is 0 and the second derivative is positive. In a multivariate case, the gradient is 0 and the Hessian has to be positive definite for minimum. If it's not positive definite, it's semi-definite, then it is not a strict minimum. Here I have an example of a multivariate case. Now we looked at this analytically. Machine learning algorithms, the way they operate is they do the same minimization using numerical methods, and I'll tell you how this numerical method works. So I given here a cartoon. For example, if you are standing somewhere here, the top of the mountain, and if you want to minimize the distance that you are from the ground, then your best solution is somewhere here, global solution, and these are all local solutions. Now what you want to do is you want to start from there and somehow come here. What would you do? So basically what we will do is we will find out directions in which I can come down the fastest, right? So these are called the steepest descent directions. So I'll try to find directions where I can come down the fastest, and then I keep walking down till I get to my solution, right? So this notion is what is called the steepest descent to get to the minimum point. So when I am standing here and I try to find a direction to go down, once I find a direction, what I will do naturally is walk in this direction for a while, and then I'll re-evaluate my direction and I'll still see whether I'm going down the fastest. If I'm going down the fastest, I'll continue in this direction, but if there is another direction which is going faster, I'll change this direction. So there are two elements to this now. One is whenever I am standing at a point, I have to find the direction in which I'm going to make the fastest progress to go down, and how far am I going to walk in that direction before I re-evaluate and then find a new direction which might be more profitable, which might get me to the bottom faster, and so on. So this notion is called the steepest descent, and this is mathematically written in the following way. If you are at a particular point x of k, you first find the direction in which you will make progress the fastest, which is called the search direction, and then you say how long am I going to walk in this direction, which is called the step length, and you walk that distance and you will get to a new point. So in this case you start with the xk. Let's say we have identified this as the direction in which I should walk, and this is the amount by which I should walk. If I do that, I'll get to this new point. At this new point, what you then do is you try and find out whether this is the best direction. If it's the best direction, you continue to go. But if you were to make a determination, this is the best direction at this point, you will again find out how long you want to walk and get to that point and re-evaluate. And if you find a new direction, you re-evaluate and so on. So in this manner, what you do is you go from the top of the hill to the bottom of the hill. So there is one which is the search direction computation, other one is the step length computation. And when you do these computations in machine learning techniques, this is what is usually called as a learning rule. So if you are talking about neural networks and backpropagation algorithm, it is basically a steepest descent algorithm. If you are doing clustering and you are minimizing an Euclidean distance, the clustering rule is again the same kind of gradient descent algorithm. So the key point is whatever be the machine learning algorithms that are used, in general they are all doing this kind of gradient descent algorithms where there is a direction and there is a step length. There are cases where you can do this much more sophisticated manner than others and so on, but the basic principles remain the same. So I have several examples here of the gradient descent and how it works, which you can kind of work with and understand. So again, I'm going to stop here for a few minutes and then see if you have any questions. If not, I'm going to conclude with some more material. Okay, so I'm going to finish with the last part for the day. I know that this is all advanced material and it takes a lot of time to assimilate and understand this. So please look through the slides, and if you have questions, you can come back later and we will be able to answer these questions. The last part which I'm going to talk about is in many data science algorithms, you not only do simple unconstrained optimization, you also do constrained optimization. For example, one of the data science algorithms, which is what is called SVM, uses this constrained optimization algorithm in its rules. So here, just to give you an idea of how this works, the math behind this, again you have to spend some time to understand this. So imagine I am trying to minimize 2x1 squared plus 4x2 squared without this constraint. So let's say first I do not have the constraint. Now clearly you can see the minimum is at 0, 0, so which is the minimum point. Now the question is, if I say I have a constraint here and then say what is the minimum of this function with respect to this constraint, but notice now here that this is an equality constraint. Okay, so when this is an equality constraint, what then it means is that whatever solution that I get for the optimization problem has to be on this line. Okay, and the question then is, clearly this cannot be the solution to this problem because this point is not on this line. So there has to be a point on this line which satisfies this constraint while at the same time minimizing this. So the way this happens is, if you take contours which are such that 2x1 squared plus 4x2 squared is a constant, and then you keep increasing the constant, then what will happen is you will get these contours. Okay, as you keep increasing the constant, these contours will keep going out. When this constant is 0, this is the point, because 2x1 squared plus 4x2 squared equal to 0 will give you x1 equal to x2 equal to 0. So these contours keep going out. So the actual minimum point for this solution will occur when this constraint just touches the contour, because if I go a little farther away, that means this constant is larger than what it was for this contour. That basically means this becomes larger than what it requires to be. So the solution to this problem will be where this line is a tangent to this contour, and that is the constraint minimum. So this is how an unconstrained minimization problem is modified when you have constraints, and in this case we talked about an equality constraint. Now we will look at what happens if I have inequality constraint. So let's say I have this where instead of, in the previous case I said this is equal to, I now make it less than equal to, in which case what we are saying is if I draw this line, any region in this is okay. In the first case when I said equal to, I just said the solution has to be on this line. Now I am saying any point to this side of the line. Remember the half plane that we talked about in linear algebra, which comes into play here. Any point on this side of the line is okay. In this case, it turns out that the original unconstrained minimization problem solution and the solution to this constrained minimum problem are the same, because the original solution falls on the correct side of the solution. Okay, so this here, what happens is the unconstrained and constrained problems have the same solution because the feasible region already includes the unconstrained solution. Now what would happen if this becomes greater than or equal to 0? It's this. Now I would like to pause for a minute and ask you to think and say where will the solution be. Clearly in this case, if I draw this, this is the region where any solution is acceptable. So this point, which was your original unconstrained minimum, cannot be a solution to this. So what happens in this case is, again you have to keep going here till you go to this side. So all of this, if you draw these contours, all of these solutions up to touching this line are okay. But if I take a solution here, the value of this constant, when I say this is equal to constant, the value of this constant is larger for this point when compared to, let's say, this point, and it is even larger when it's here. So in this case, what you need to do is you need to keep looking at this and then say, when will this contour just touch this line so that it just becomes feasible, and that is the best solution. And you will notice that this is the case where this solution is the same as the solution when you had this equal to. So this is the way in which constraints modify the optimization problem. Now this is one simple constraint and a simple objective function. Now if it turns out that there are many constraints and the objective function is more complicated, how would someone codify all of this into an optimization algorithm is what is given by what we call as this Karush-Kuntakar conditions. This is much more complicated than the simple geometric example that I showed, but basically these conditions are the ones which ensure that our geometric understanding is codified into math, and when you have many more constraints and the objective function becomes a lot more complicated, you can systematically use these conditions to find the optimum solution for unconstrained and constrained optimization problem. Now in many machine learning algorithms, these kinds of conditions are used in deriving the learning law, as they say, and that's the reason why we looked at this. Now you need a lot more understanding of this to be able to understand data science algorithms in a lot more detail if you want to take an optimization view of data science and understanding data science from an optimization viewpoint. So in summary, I would say what I have tried to do is to give you the things that you should learn in terms of being able to understand data science better. So if you think about what are the mathematical foundations that underlie data science, I would say you need to have a very good idea of linear algebra, and the topics that I outline are very important topics. You might want to understand those very well. And the statistics, hypothesis testing, the notion of random variables, discrete random variables, continuous random variables, and so on, those things that we talked about, you need to have a good understanding of that. And in terms of optimization, even if you don't spend too much time on constraint optimization, at least the notion of unconstrained optimization and the gradient descent algorithm is something that you should be very familiar with. Once you understand all of this in reasonable detail, then you would be ready to understand machine learning algorithms in little more depth than just applying them for problems and so on. So I know that this is quite a bit of material, quite a bit of advanced material, but like I said before, we are trying to do this in 6 hours. Given that constraint, I think what we are really trying to do is tell you what are the things that you need to learn in more detail to be able to get into this fascinating field of data science. So what we will do is in the next lecture, to make some of these come alive, we will two data science algorithms. Conceptually, I will explain those, and then we will do a case study which you will yourselves do to do one data science problem, which hopefully will open up more ideas and more interest to learn data science in lot more extensive detail. So I'll see you guys again Monday next week to do the last 2-hour session. If you have any questions again, I'll be happy to answer. I'll wait for a couple of minutes and see if you have questions. If not, I'll see you again next Monday. you.